the tradition of the Aspen Center of Physics Summer Colloquia. We continue this, COVID, no COVID, and it has been a very successful series. I want to acknowledge the Aspen Center for Physics Administration and also the committee for the colloquia run by Martin Elvis, the chair at Harvard. There has been a very successful series already with overwhelming participation this summer with a range of topics. And today, I, as a member of this committee, of the Colloquium committee, I was asked to introduce my good friend and colleague, André de Gouvêa, from Northwestern University. I will do a small introduction, but before I do the introduction, I want to say that I have worked in various committees, including the Physics Advisory Committee of Fermilab, and there has been not a single time that I have not learned something from André in the past maybe 7 years or so that I have been involved with various physics, the physics program of Fermilab and the physics program in general of high energy physics, be it collider or be it neutrino. So André did his PhD at Berkeley, and then he concentrated on phenomenology, on high energy physics phenomenology, beyond the standard model, and various indirect and indirect searches for physics beyond the standard model, including dark matter. In the past years, he has been very much a critical player in the program, in the neutrino program, in the phenomenology, and different kind of model making, and in the program for the next big neutrino project in the US and international now. As you know, CERN has been participating with significant effort in the ProtoDune that has produced already significant results as a pilot and a pathfinder towards the big Dune LBNF project. And without further ado, he's going to tell us about the Brave New World. Now, the protocol is we reserve all questions for the end, and we are going to be keeping the track of raised hands in order to go through the questions. And at this point, the recording has started for those who asked for that. And André is going to take over the stage and start with this colloquium. Thank you.
Okay, well, so thank you, Maria. Thanks the Aspen Center for Physics for the invitation to give this talk. So my job is to tell you something about neutrinos. This talk is aimed at a very broad audience. So I see some particle physics people in the audience, and my job is to make sure that you're very disappointed with the talk. So I will tell you something about neutrinos, and let me just get started right away. Just so that everybody's on the same page, I want to remind you the fact that neutrinos are among the handful of fundamental particles that we've identified in the world of particle physics. And again, particle physics is all about studying the fundamental particles. So I will be telling you about a very, very small subset of those fundamental particles, the neutrinos. And in case you're wondering, they look like this. And I hope you can see the little hand on my screen. If you can't, it'll be a problem and I won't do anything about it. So again, this is aimed at getting people up to speed. If you haven't heard about neutrinos, neutrinos are probably the second most abundant particles in the universe. They are incredibly abundant and they're produced absolutely everywhere. The story that everybody likes to tell is that neutrinos are actually produced in the sun all of the time. So the sun is an amazing neutrino factory. And people like to talk about the flux of neutrinos coming from the sun. And the flux is about 100 billion per second per square centimeter. That means that if you raise your thumb, you get about 100 billion neutrinos from the sun every second. Now, neutrinos are not just produced in the sun, they're also produced in a lot of radioactive processes. They are produced in large abundances in nuclear reactors, and they're also produced as cosmic rays hit the atmosphere. Something that people like to talk about is, again, there's a whole bunch of very vanilla radioactive processes that produce neutrinos. So here's another one of these random facts that you probably want to pay attention to if you're talking to your non-physics friends. If you take a generic banana, the generic banana probably produces about 1 million neutrinos per day. So if you didn't know that, then now you know. And of course, neutrinos are also produced in a very, very large number in catastrophic astrophysics sources. For example, when a supernova explodes and it emits a gigantic amount of energy that we can see from ridiculously far away. This is a picture of the supernova 1987A that exploded in 1987. And you see the picture on the left is the result of the explosion, and the picture on the right is the before picture. But the impression that you want to leave with when you stare at this picture is that if we could see this picture in neutrino brightness, the amount of energy that gets released in neutrinos is about 100 times bigger than the amount of energy that gets released in photons. So a supernova explosion to zeroth order is a very, very efficient way of converting gravitational energy into neutrinos. And I think I just mentioned this as well. Neutrinos are also known to be relics of the Big Bang. We've never seen a neutrino from the Big Bang, but we have a lot of evidence that they are around by the way in which the universe has been expanding as a function of time. If the neutrinos are not there, we will be amazingly surprised, because all of our fits to data are consistent with the existence of neutrinos from the Big Bang. And again, the number that you probably know about if you're in, for example, cosmology and astrophysics is that the ratio of, say, protons to photons in the universe is about 1 in 10 billion. And the number of neutrinos which are left over from the Big Bang is about the same as the number of photons from the Big Bang. So neutrinos and photons, they outnumber all of the other more boring particles by about a factor of 10 billion or so. So again, you know, if you wanted to describe the universe to your friend, the universe is mostly a large collection of neutrinos and photons with a little bit of some other stuff that's not very important. Of course, if you're new to the field of neutrino physics and you've never heard of them, you might be surprised to learn that they're everywhere. And you might be asking, how come I never knew about this? And the reason is, of course, that neutrinos are incredibly hard to detect. They're called neutrinos because they're neutral. There's actually a very long story, which I won't tell you, but they don't have any electric charge, which means that they are immune from interacting via the electromagnetic force, like the electrons, for example. And even if you look at other neutral particles like neutrons, neutrinos are even harder to interact than those particles because they don't see the strong nuclear force either. It turns out that the neutrinos only see what's called the weak force. And it turns out that the weak force is actually very weak for the types of energies that we normally care about. And that's why neutrinos are so hard to detect. There are a couple of nice numbers to keep in mind if you've never thought about this. One is, I told you that the sun is this gigantic factory of neutrinos. So if you wanted to prevent any of those neutrinos from ever hitting you, you could shield them. But in order to shield the neutrinos from the sun, you need about a wall of lead, which has about the thickness of the solar system. So it's very difficult to shield neutrinos. There's another nice number to keep in mind, which is if you look at the solar neutrinos, there's a whole bunch of them going through your body all the time. And it turns out that if you live a long life, it turns out that during that lifetime, you'll probably get hit by one neutrino. So if you get lucky, you might be hit by a neutrino once in your entire lifetime. Again, if you're not in physics and you're worried about this, you shouldn't be, because we get hit by a whole bunch of other stuff all the time, and we're still here. At least I'm here. So anyway, so neutrinos are incredibly hard to study in spite of the fact that they're very common. And you can ask, how do we ever get to study neutrinos at all? And the reason is that we're very creative, and we can actually construct gigantic detectors that take advantage of these very, very large fluxes. So again, you know, a detector the size of a person is not a very good detector because it will only see one neutrino event every 100 years or so. But if you build a detector which is 100 times bigger than a person, then you actually get to see about 1 event per year. And if you build something that's 10,000 or 100 times or 1,000,000 times bigger than a person, then you start getting enough events that you can start studying those neutrinos. And that's what we've been doing for the last several decades, ever since we figured out that neutrinos existed. So I'll give you a very quick summary of everything we figured out about neutrinos until about the end of the 20th century. And I will say this concentrating on things which are actually important for us. One is that neutrinos actually come in a threesome. And that's true of all the other matter particles that we know about. So we know that there are 3 kinds of neutrinos. We call them flavors. And we label the neutrinos according to what's the charged lepton that gets produced along with them when there's a weak current interaction. So the neutrinos participate in these weak interactions, or something called the charged current interactions. And whenever there's a charged current interaction, that's an interaction between a charged lepton like the electron and the neutrino. So whenever the charged lepton that's involved in the interaction is the electron, the neutrino that's also involved in that is called the electron neutrino. It turns out that the electron has a couple of heavier friends. One is called a muon. The muon is exactly like an electron, but it's heavier. And then the other one is called a tau lepton. And the tau lepton is just like the electron and the muon, but it's also heavier. And it turns out that a neutrino is produced along with the electron is referred to as the electron neutrino. A neutrino that's produced along with the muon is called a muon neutrino. And the neutrino that's produced along with the tau is called a tau neutrino. Over the many decades, we went through the exercise of figuring out if those neutrinos are actually different states. And the answer is yes. And the reason is that when an electron neutrino hits something, it only knows how to produce electrons. When a muon neutrino hits something, it only knows how to produce muons. And when a tau neutrino hits something, it only knows how to produce taus. Again, going down this list, until the end of the 20th century, we were pretty sure and we were very happy with the idea that neutrinos had 0 mass. And there's another funny feature that I want to spend a couple of minutes talking about, which is it turns out that the weak interactions, and this has been known for a long time, they really violate parity very violently. And when it comes to neutrinos, this parity violation is very easy to see for the following reason. It turns out that all experiments we've ever done to date, all of the neutrinos that have been produced are exactly left-handed. Left-handed as in their helicity is minus, or their left-handed helicity. And all of the anti-neutrinos that have ever been produced are right-handed. And this is an experimental fact, and we have never observed any violation of that fact. So curiously enough, and I'll come back and talk about this, if you never thought about describing a massless fermion, massless fermions are weird, and I'll talk more about this later. But the point I'm trying to drive home is that as far as observations are concerned, we have only seen 2 states of the neutrinos. One is a left-handed state that we call the neutrino. The other one is the CPT conjugate of that, which is a right-handed anti-neutrino. Now, finally, the neutrinos also seem to have a quantum number that's called Lepton number. And the idea is the following. If you assign all of the neutrinos and all of the charged leptons Lepton number plus, and you assign all of their antiparticles Lepton number minus, if you ever do any experiment ever, the amount of leptons going into some reaction is the same as the amount of leptons coming out of the same reaction. And this is something we've never seen be violated. So the reason I'm giving this talk is that that story that I just told you before turns out to be a lie. It's wrong in a few important ways. And what we have found out on our way to the new century is that it turns out that this picture here is only approximately correct. And what we found out is that if you produce what we think is an electron neutrino and we wait long enough to detect it, when we detect it, it has a non-zero probability of being detected as a different flavor. So basically what we have found out by doing a whole different kinds of experiments is that it is possible to produce a muon neutrino and have it be detected as a tau neutrino. It is possible to produce an electron neutrino and have it be detected as a muon neutrino, and so on and so forth. And the evidence for this has been mounting over the last several decades, and it's absolutely overwhelming. And the key points here is that this phenomenon depends on the neutrino energy, and it depends on how long you wait until you detect the neutrino. We normally express this in terms of what's called the baseline. And if we wait long enough, then the neutrino can undergo this phenomenon of flavor change. And it turns out that if we look at all the evidence for this phenomenon, the only way we can explain this satisfactorily is by postulating that neutrinos have non-zero masses. So in some sense, if we boil down what we've discovered is that we've discovered that neutrino masses are not zero. I want to spend 1 minute talking about how this happens, because it's a fun thing for physicists to understand because it's very easy. And the idea is very simple. Imagine that I tell you that now we know that neutrinos have mass. And let's give the neutrino masses some names. And the names that we've come up with are mass number 1, mass number 2, and mass number 3. And these are not very clever names, but these are the names. And of course, the neutrino that has mass number 1 is called nu1. The neutrino that has mass number 2 has mass nu2. And the neutrino that has mass number 3 has mass nu3. It's called nu3. So I also told you before that we can also identify what are called the neutrino flavors, the electron neutrino, the muon neutrino, and the tau neutrino. And the question is, what's the mass of the electron neutrino, or what's the mass of the tau neutrino? And the answer is that the electron neutrino, the muon neutrino, and the tau neutrino don't actually have a well-defined mass. If you think about it a little bit harder, the electron neutrino, the muon neutrino, and the tau neutrino are actually not even particles. They are interaction eigenstates. And the right statement that we would like to make is to say that the electron neutrino, the muon neutrino, and the tau neutrino are quantum mechanical linear superpositions of the neutrinos with a well-defined mass. And because the electron, muon, and tau neutrinos are different states, they are orthogonal linear superpositions of the neutrinos with a well-defined mass, which means that if I write down this equation here, which I'm trying to highlight with my little hand here, the coefficients that relate the electron, muon, and tau neutrinos to the neutrino number 1, 2, and 3, they form a unitary matrix. Okay, so that's the idea. So that's a statement number 1, which is that if the neutrinos have mass, the interaction eigenstates don't have to be aligned with the flavor eigenstates. And this is very important because even though the neutrinos are produced as interaction eigenstates, they propagate as mass states. So the eigenstates of the neutrino propagation Hamiltonian are these mass states. And the idea of why this is so important is that this is a cartoon of what would happen in the world if we only had 2 neutrinos. So that means we would say that the electron neutrino is a linear superposition of nu1 and nu2 with coefficients cosine theta and sine theta. And the muon neutrino is also a linear superposition of nu1 and nu2 with coefficients which are minus sine theta and cosine theta, in a way that the electron neutrino and the muon neutrino are orthogonal states. Now the key point is, as these neutrinos, which are produced as a linear superposition of Hamiltonian eigenstates, propagate, the different components of the neutrino pick up different phases. And this is a phenomenon that everybody knows about. If you ever studied a 2-level system in quantum mechanics, which I hope everybody did, because that's the easiest problem you can solve in quantum mechanics, you know that then as this system evolves, because these different components of the state pick up a different kinematical phase, you no longer have the system that you started with, but your system now has changed. And we can go through the calculation of how this works out. And I'm not going to go through this in detail here. I just want to make a couple of comments. One is when we talk about neutrinos propagating in the laboratory frame, the neutrinos are always, always, always ultra-relativistic. That means that their energy is much bigger than their mass. So we're going to make an ultra-relativistic approximation. And when we do that, we can calculate what's the probability that a neutrino is born as an electron neutrino, but is detected as a muon neutrino. And we get a formula that's very familiar to people that have worked out things like Rabi oscillations in two-level systems. And we get a sinusoidal behavior, and the amplitude of the sinusoidal behavior has to do with this angle theta that relates the nu e and nu mu basis to nu1, nu2 basis. And the frequency of the oscillation is related with the differences of the neutrino masses squared. Okay, and we understand why this works out that way, but this is what we want to remember. And of course, it's also proportional to the distance that the neutrino propagates divided by the energy of the neutrino, which is related to the proper time of the neutrino if you were actually doing this calculation in the neutrino rest frame. So this is what oscillations look like. So you start out with an electron neutrino, and if you wait long enough, there's a non-zero probability that you'll be detected as a muon neutrino, and then this thing oscillates, and this phenomenon is called neutrino oscillations for completely obvious reasons. And the key point is, by measuring neutrino oscillations, we can learn a lot about neutrinos, including we can measure their differences of masses squared, because the frequency of this oscillation is proportional to the neutrino delta m squared. And we can also measure these mixing coefficients, which are called the mixing angles, by measuring the amplitude of the oscillation. This turns out to be correct, except that we have to do it assuming, keeping in mind that there are 3 neutrinos. Again, this is a picture of what that looks like. So the nu e and the nu mu and the nu tau are linear combinations of nu1, nu2, and nu3. And those linear combinations can be parameterized as a 3x3 unitary matrix. And as far as oscillations are concerned, the number of physical parameters that describe neutrino oscillations are going to be 3 mixing angles and 1 complex phase. And the mixing angles are called the theta 1,2, theta 2,3, and theta 1,3. And this phase is called a delta. And I will show you a little picture of what all of these parameters mean in terms of physics. Before I do that, I want to give you a sense of how much progress has been made, at least in my physics career, which has been relatively long in some units. But the point is, after about 20 years of vigorous neutrino oscillation research, we have measured almost all of these parameters quite well. Some of them are measured at the few percent level. The one that we haven't measured very well is this CP odd phase delta, which I'll talk about. And the thing that's most impressive about looking at this table, which has a bunch of numbers in it, is that when I started graduate school, we didn't even know these numbers existed, let alone we could measure them at the few percent level. So the amount of progress that has gone on in neutrino experiments, especially if you keep in mind the time scales of particle physics, has been sort of breathtaking. And we still have a lot of work to do. Here's kind of a picture of what these mixing parameters mean and what haven't we done yet, because you've probably heard about neutrino oscillation experiments for a while, and you might be wondering, why are we still doing this? And I'll try to give you a sense of that. So this picture here is a picture of the neutrino masses squared in the way in which they're ordered. And it turns out that we know that in absolute value, the neutrino masses squared are hierarchical. So there's one neutrino mass square that's small, and then there's the other neutrino mass squared, which is large. So this is the small separation between 2 states, and this is a large separation between 2 states. And it turns out that given the data that we have, we don't know exactly how the neutrino masses are ordered. We don't know if the 2 states that are close together are separated from a heavier state, or whether the 2 states which are close together in mass are separated from a much lighter state. the data that we have access to today, can't tell those two pictures apart. The one on the left is called the normal ordering, and the one on the right is called the inverted ordering. And the reason for that is that if you have the normal ordering, it is possible that the lightest neutrino mass is much lighter than the second lightest neutrino mass, which is much lighter than the third lightest neutrino mass. And the reason we think that that's normal is that that's what happens, for example, with the charged leptons. That's also what happens with the quarks. On the flip side, if the neutrino mass ordering is inverted, it is possible that the lightest mass is much lighter than the second lightest mass, but then the heaviest mass is almost degenerate with the second heaviest mass. And that's called an inverted ordering because it's the opposite of what we think is normal. Okay, so if you ask, oh, and then the other thing that's worthwhile to appreciate here is that you notice that these bars have colors in them. And those colors represent, if I can do this, no, yes, I can. They represent the entries of these elements of the mixing matrix squared. And there's an interpretation to that, which is if you could isolate a neutrino number 1, and you asked what's the probability that the neutrino number 1 will behave like an electron neutrino once it's detected, that probability is a UE1 squared, which is colored here as the fraction of this bar, which is colored red. Okay, so these are the questions that we're asking. So what haven't we measured yet? What we haven't measured yet is a CP violation, and I'll say something about that in just a minute. The other thing that we haven't measured is we don't know which one of those two pictures is correct, the normal hierarchy or the normal ordering and the inverted hierarchy or the inverted ordering. And clearly the picture has to look like one of those and it can't look like both of those at the same time, but we haven't figured out what the right picture is. And finally, the last thing that we haven't measured yet has a physics interpretation to it, which is a little bit weird, which is the following. If you look at all of the states here, in particular, if you look at this neutrino number 3 state, which is this one, you will notice that the way that I drew that, the amount of the bar that's colored green and the amount of the bar that's colored blue is about the same. So it turns out that we don't know if the amount of green is bigger than blue or vice versa for the neutrino number 3 state. That's associated with one of the parameters that we have. It's one of the mixing angles. And the question we like to ask is that mixing angle maximal or not? So these are things that we haven't measured yet. And what's fun is we know that we can measure them by doing neutrino oscillation experiments. So it's not a surprise that we're doing neutrino oscillation experiments because there are well-defined questions that we can ask that we don't know the answers to yet. I do want to highlight that if you've listened to a neutrino talk before, you probably have heard people listing all the things that we haven't measured yet. And if you're not a particle physics enthusiast, you might think that just measuring a bunch of parameters is kind of boring. It's the sort of thing that particle physicists care about. But I shouldn't care about that if I'm not a particle physicist. And what I do want to remind people of is the fact that the reason we're learning more about neutrinos is not just to measure a whole bunch of numbers better, but we're really still in the process of figuring out if we've actually gotten the story straight or not. You know, do we actually have the right model? You know, we have stumbled upon a new phenomenon about 20 years ago. We came up with a model that explains this new phenomenon. But the question is that really the whole story? Or is there something that we're missing? So that's what we're in the business of. We're in the business of not just measuring a whole bunch of parameters, but making sure that we've gotten the story straight. And I like to show this picture. This phenomenon of mixing is not new or unique to neutrinos. It also happens in the quark sector. And it turns out that in the quark sector, we can also measure the mixing parameters. And here are two of those mixing parameters. They're called rho and eta. We put bars on top of them just to confuse people. But anyway, if you look here in this plot, there's a whole bunch of curves. And every one of these curves is a different measurement. And it's a different measurement of the same two parameters. And again, you can ask, why would people go through all this trouble of doing all these different measurements of the same two parameters? And again, these are not cheap measurements. These are expensive measurements to make. You know, we have to build these gigantic accelerators to make a lot of these measurements as precisely as we have. And my plot is actually old. This is a 10-year-old plot. There is a 2020 version of that, which looks just the same, but the error bars are smaller. And the reason we do this is not to measure the same parameters in 5 different times, but to actually ask if we get the same answer all the time. Because if we actually got a different answer by doing 2 measurements of the same parameter, that would indicate for us that the model is wrong. Because every time you measure a parameter, there's an implicit assumption that the model is correct. So in the quark sector, we've actually done this, you know, in 20 different ways. And I'm sad to report that we actually always get the same answer. So the answer is this point over here, where there's this little potato-shaped object in the middle of the plot, which means that as far as the quark sector is concerned, the weak interactions and this mixing seems to work really, really well. So our job in the neutrino sector is to do something similar. I mean, we want to be able to measure the same parameters in lots of different ways and make sure that we actually get the same answer every time, because if we don't, it would be a big indication that there's something missing in our measurements. And I want to go back to this matrix here just to remind people that even though I told you that we've measured all of these parameters at the few percent level, that's kind of a lie. And the reason is that when we measure these parameters at the few percent level, we actually make an assumption. And we make a whole bunch of assumptions, including the fact, for example, that this matrix here is a unitary matrix. That didn't have to be true. And if it's not true, the precision with which we can measure these entries of the matrix is completely different. And in particular, I want to remind people that if you look at the way I drew this matrix, you notice that some of these elements here have colors like red and blue and green. And the reason they have these colors is just to remind us that what we really measure is the absolute value squares of some of these colored elements. For example, we've never measured any of the black elements in this matrix, for example. So we have a long way to go to test if this matrix is actually unitary or not. So I will give you a list of, okay, so I told you the story, you know, there's weak interactions, the neutrinos mix, but we're not sure that that's the whole story. So the question is, so what could the story be that's different from the story that I'm just telling you? What could we be missing? And the key point I want to impress upon you is the fact that once you allow the leptons to mix, and once you allow the neutrino masses to be non-zero, there's a whole bunch of stuff that could be going on that could show up in these oscillation experiments. Now, again, it doesn't have to be true, but our job in physics is not to bet what the right answer is supposed to be, but our job is to figure out what the right answers are. And I'll give you a very incomplete list of stuff that could be happening because we've uncovered neutrino oscillations. So for example, it is possible that there are more neutrinos than we know about. That would mean that the mixing matrix is bigger than 3 by 3, which means that the 3 by 3 submatrix is actually not unitary because it's part of a bigger matrix. It is possible that the neutrinos have more interactions than we know about. And if that happens, that changes the way in which the neutrinos oscillate. And, you know, neutrino oscillation experiments could reveal that. It is also possible that the neutrinos have other properties that we don't know about. And actually, the neutrinos have some more properties that we don't know about, but we're sure that they do. And a couple of those are surprising if you haven't thought about neutrinos for a while. One is, first of all, the neutrinos must have a non-zero magnetic moment. That means that they have to couple to photons. And that statement is only true because the masses are not zero. If you don't know why that is, I'll let you think about it. And the other one, which is easier to understand, is there are 3 neutrinos. At least 2 of them have mass. And since they have weak interactions, all of the neutrinos that are the heaviest ones have to decay into the lightest one. They are not protected by anything. That means that all neutrinos have a finite lifetime except for the lightest neutrino. And within the weak interactions, we can calculate what the lifetime is supposed to be. It's like 10 to the 40 years, which is a long time. But on the flip side, if you look at our ability to constrain the neutrino lifetime by doing robust experiments, the bounds on the neutrino lifetime are like a millisecond. So we have a prediction that's 10 to the 40 years. We have a lower bound, which is like a millisecond. So there's a lot of room for stuff to be going on. And then the other thing I want to say is the neutrinos do undergo oscillations, which is a quantum mechanical phenomenon. So there's a whole bunch of weird quantum mechanics questions you can ask of the neutrino system that could show up by doing neutrino oscillations. Okay, I want to say a few words about CP violation. I'll do that quickly. One thing we can do is we can look for nu mu to nu e oscillations, and we can compare that with nu mu bar to nu e bar oscillations. And if the answer turns out to be different, that means that CP is violated in a very, very textbooky way. That means, you do something with matter, you do something with antimatter, you get a different answer. That means that matter and antimatter behave differently. If you're not familiar with CP, the P part is the fact that the nu mu's are always left-handed and the nu mu bars are always right-handed. So I want to give you an example of what things could look like. This plot here on the bottom, that's a cartoon of whether we could measure, say, nu mu to nu e oscillations compared with nu mu bar to nu e bar oscillations. And they could look actually quite different. This is a cartoon where I've picked typical values for all of the parameters, and we could be living in a world where the differences between neutrino oscillations and anti-neutrino oscillations are quite big. And this is one of the main goals of the current batch of neutrino experiments and the upcoming new generation of neutrino oscillation experiments. So this is something we would like to do. And in the scenario that I showed you, the parameter that governs how much neutrino oscillations and anti-neutrino oscillations are different is this delta parameter. And the stop plot here that I want you to look at is how well we've constrained this delta parameter. It's a phase between 0 and 360. And it's fair to say that, I guess, magenta colored contour or pink contour, depending on how well you can tell colors, that's a 3 sigma contour. That means that at the 3 sigma level, we mostly don't know what this CP violation parameter is. We don't know whether CP is violated or not. So we still have some work to do. I want to skip this. I want to say a few words about what the CP violation mean and why we're so excited about that. And the reason is in particle physics, people discovered CP violation a very long time ago, and that's in the quark sector. And all CP violating phenomena that we've ever observed are governed by the equivalent of this delta phase in the quark sector. We call it the phase in the CKM matrix. So that phase, as far as we've ever determined, is a large number. It's like, I always forget, 70 degrees or some number like that. It's a big number. We don't know where that number comes from, but it's a number in our Lagrangian. It turns out that there's another phase that we don't like to talk about, which is called the strong CP phase. That's another phase that could be there in our Lagrangian, but we've never seen that phase. We've only constrained it to be some ridiculously small number, like 10 to the minus 10 or something like that. We don't know why that number is very small either, although we have some ideas of why that's very small. So basically, before we discover neutrino masses, the number of CP violating parameters in the Lagrangian is 2. One of them is pretty big. The other one is ridiculously small. With the discovery of neutrino masses, it turns out that the number of CP violating parameters is at least 1 more. And it could be 3 more, depending on whether the neutrinos are Myron or fermion, which I'll say something about in a few minutes. And we have absolutely no idea what that parameter is supposed to be, but we do know that we will increase our knowledge of CP violation by at least 50%, which is very exciting. Whenever you get 50% more information, we should be excited about that. And I do want to remind people who like to guess that probably CP violation in the neutrino sector is very large, that in the past, we tried to guess what the other parameters were supposed to be. In particular, we made a bunch of guesses about what the mixing angle should be, and we were completely wrong. So any guess that you can make about what the CP violating parameter is supposed to be is a pure guess, and we have to defer to experiments as we should always do in physics. So again, we have a whole bunch of new experiments coming online to study neutrino oscillations. This is a list of what they are. They all have different names. There are experiments in the US, in Japan, in China, in the South Pole. And they're all aimed at giving us more information on neutrino oscillations, which will allow us to not only address the stuff that we haven't measured yet, but also test whether the model is right. So the last couple of things I want to say something about are what else don't we know? And one thing that's important to appreciate is the fact that when you do neutrino oscillation experiments, you only measure the differences of the neutrino masses squared. So in reality, we don't really know what the neutrino masses are at all. We do know, for example, excuse me. We do know, I don't know what happened. My voice almost went. Okay. We do know that the lightest mass has to be at least a 0. But if the lightest mass is 0, we have very hierarchical masses, probably. But it's also possible that the lightest mass is big enough that all neutrinos' masses are almost degenerate. And those two hypotheses are not ruled out. And one of them has to be true. Now, we need experiments that are not neutrino oscillation experiments in order to get the answers to those. And we have some handles on it. The most promising handles are probably measurements of beta decay and cosmology. And I'll say just a word about those two. And beta decay is a very simple idea. So the neutrinos were postulated by Pauli. Neutrino interactions were described phenomenologically by Fermi a little bit after that. And Fermi said that he even had a plan for how to measure neutrino masses, and the plan is a good plan. You look at some beta decay process, and then you ask, okay, what's the largest possible energy that an electron can have? And if you calculate the largest possible energy an electron can have, that energy is related to the Q value of the process and the neutrino mass. So the idea is if you can measure beta decay very, very precisely, and you look at the endpoint of the beta that comes out, the shape of the endpoint of this spectrum is impacted by the neutrino mass. And that's shown, for example, in this plot here on the right, where the red curve is what the shape looks like if the neutrino mass is 0. The blue curve is what the shape looks like if the neutrino mass was some number like 1 electron volt. And you notice that the shapes are different. So by studying the shape of the endpoint of the neutrino spectrum, you can actually get a lot of information on the neutrino masses. If you are a technically minded person, the thing that we actually can measure by doing this type of experiment is a linear combination of the neutrino masses squared. And that's the linear combination that's here in red. And it's proportional to the elements of the mixing matrix squared, which we have measured, and the masses, which we haven't measured, but we know the differences of them. And this quantity here is called the effective electron neutrino mass, in spite of the fact that the electron neutrino is not a particle and doesn't have a mass. But I just wanted to emphasize that. So anyway, we're in the process of learning more about this. I'm required to show you this picture. There's an experiment aimed at measuring tritium beta decay as precisely as possible. It's taking data as we speak. It's called the Katrin experiment in Germany. And it is actually a spectrometer. And this is the size of the spectrometer. And it's a gigantic object which has now been installed, and it's running and taking data. And people can ask me why it looks like this and why is it so big if they're curious, because I don't want to spend too much time talking about that. Finally, the last thing about direct neutrino masses that I want to say is that, as I said, the neutrinos are relics from the Big Bang. They change the way in which the universe expands. And just to tell the story very quickly, the neutrinos are also a special kind of a relic of the Big Bang, because when the universe was very hot, the neutrino masses were completely irrelevant. So neutrinos behave like radiation. When we get to today, the universe is so cold that even the heavy neutrinos are cold. So the neutrino is a kind of relic of the Big Bang that changed its behavior from radiation to matter relatively recently. And that leaves an imprint in the large-scale structure of the universe. So by looking at the large-scale structure of the universe, we are sensitive to the neutrino mass. We haven't seen the effect of a non-zero neutrino mass yet, but we have been able to place an upper bound on the sum of the neutrino masses. And this upper bound is less than about 0.2 electron volts. Now, this is an indirect measurement, and you can screw around with that in lots of different ways by either changing cosmology or by changing the properties of neutrinos, but it is a very non-trivial bit of information. And what people are very excited about is that we're pretty sure that in the next 5 or less than 10 years, that the precision of these very large cosmic surveys will be good enough that if our story about neutrinos is correct, we must see evidence of a non-zero neutrino mass, even in the worst case scenario. And I don't want to explain what this picture is about, but people can ask me later. But it basically means that even if the lightest neutrino mass is as light as possible, which is 0, cosmic surveys will be sensitive to non-zero neutrino masses at more than the 3 sigma level in the next 5 to 10 years. So this is a space that all of us like to watch very, very carefully. Okay, the last thing I will talk about, because this has gone very slowly, is the last thing we don't know about neutrinos is what is the nature of neutrinos? And that's a question that we can ask of neutrinos that we can't ask of other particles. And it has to do with whether the neutrinos are what we call Dirac fermions, or whether they are what we call Majorana fermions. And I will try to explain what this means. And I apologize again to people that know this very, very well, but it's a topic that's very confusing. And I'll try to explain it in a way that will be confusing, but hopefully confusing in a different way. And this will be probably the end of the talk. But so just to be very concrete, let's talk about electrons. We all know about electrons. They're our favorite particle. We've known about electrons since the 19th century. So imagine you knew nothing about electrons, but you discovered one in your laboratory, and you actually even determined that it was left-handed. So you see a left-handed electron in the laboratory, which is great. So you've discovered a new particle. You should be excited. So what else do you learn about this state, the left-handed electron, if you make that discovery? The first thing that you discover is, because of the CPT theorem, you know that positrons exist. And because the thing that you discovered was a left-handed electron, you know that right-handed positrons also exist. So again, you discover a second particle for free. Now, let's say that you keep doing experiments with this electron that you've just discovered, and you discover it has a mass. What this means is that the electron has a rest frame. And that means, of course, that if you can see an electron with spin up in the electron's rest frame, you can definitely see an electron with spin down. That means that if left-handed electrons exist, that means that right-handed electrons also exist. And if right-handed electrons exist, that means that left-handed positrons also exist. So the end of the story is, if you want to describe a left-handed electron that has mass, you know that that same object that you're going to use to describe that actually describes 4 degrees of freedom. And they're going to be the 2 spin states of the electron. Here we're calling them left-handed and right-handed. And the 2 spin states of the positron, which here we're calling right-handed and left-handed. So that means that, to summarize the story, the electron has 4 degrees of freedom, or it requires 4 degrees of freedom to properly describe this electron. Now let's talk about neutrinos. So we know about left-handed neutrinos. And again, because of the CPT theorem, we know that right-handed antineutrinos must also exist. And these, by the way, are the particles we can see in the laboratory. Now, we've discovered that neutrinos have non-zero mass. That means I can go to the neutrino rest frame, And of course, if you see a neutrino with spin up, you're going to be able to convince yourself very quickly that there must be another state which is a neutrino with a spin down. Or that means if you have a left-handed neutrino, a right-handed neutrino must also exist. And here's where the neutrinos are special or different. And they're different in the following sense. This analysis that I'm just trying to make is because the neutrinos have mass, a left-handed helicity state and a right-handed helicity state must exist. But if we look at what the CPT theorem is telling us, it's telling us that there is this left-handed state, and there's also this right-handed antineutrino state that we know exists because of the CPT theorem. So the question then becomes, is it possible that the right-handed neutrino state is actually the right-handed antineutrino state in disguise? Or is it possible that this right-handed neutrino state is another degree of freedom? So saying this in other words, is the Lorentz partner or the up and down spin partner of the neutrino the same as the antineutrino, or is it a different particle? And notice that when we were talking about the electron, this confusion never comes up because the left-handed electron is a CPT friends with the right-handed positron, and the right-handed positron and the right-handed electron have different charge. So we will never confuse them as being the same particle. But because the neutrinos have no charge, it is possible that we would get those two confused. And we don't know whether the neutrino then has 2 degrees of freedom, a left-handed one and a right-handed one, or whether they have 4 degrees of freedom, a left and right-handed neutrino and a left and right-handed antineutrino. So again, to summarize, we don't know if the neutrinos have 4 degrees of freedom or 2 degrees of freedom. That's the question that we don't know the answer to. If they have 2 degrees of freedom, they're called Majorana fermions. If they have 4 degrees of freedom, they're called Dirac fermions. And I do want to say that 2 and 4 are very different numbers. So you should be surprised by the fact that we can't tell 2 from 4. And there's an answer to that. And the reason is that even though we've discovered that the neutrino masses are not 0, the neutrino masses are very, very small. And what happens is there's a flaw in this argument that I was trying to make, which is this argument breaks down if the neutrino mass had been exactly 0. If the neutrino mass is exactly 0, it turns out you can't ask if the neutrinos are a Dirac or a Majorana fermion. It's not a question you're allowed to ask. It's a non-physics question because there's no distinction between those 2 states if the mass is exactly 0. What this means in terms of physics and in terms of experiments is that if you can find an observable that can answer the question, is the neutrino or Majorana or a Dirac fermion, you better not be able to get an answer if the neutrino mass is 0 because you can't ask the question. What this means in terms of numbers is that this observable is proportional to the neutrino mass in the way that the observable must vanish when the neutrino mass goes to 0. And that's the problem. The neutrino mass is really, really tiny. So the probability or this observable that can distinguish if the neutrinos are Majorana or Dirac fermion is always an absurdly rare observable. And I don't want to talk about this because I've run out of time. But I do want to say that we do have a favorite observable for determining if the neutrinos are Majorana or a Dirac fermion. And it's actually a nuclear physics process. It's called the Neutrinoless double beta decay. And it's a process where you have a nucleus that decays into another nucleus and emits 2 electrons. Now, why do we care about that? We care about that because of something I forgot to say, which is if the neutrinos are Majorana fermion, then the neutrino and the antineutrino have all exactly the same quantum numbers. That means that they can't have any quantum number that has a plus or minus for particle and antiparticle. This includes lepton number. That means that if the neutrinos are Majorana fermion, lepton number is not a good symmetry of nature. It must be violated. And any physics process that will reveal if that lepton number is violated will also reveal that the neutrinos are Majorana fermion. And that's what neutrinoless double beta decay does. And We've been looking for this for a long time. The thing that's very exciting is we can calculate the rate for neutrinoless double beta decay if the neutrino is a massive Majorana fermion. As I advertised, the probability for that to happen is proportional to the neutrino mass, and it's actually proportional to some linear combination of neutrino masses. And what's very exciting is because we know something about neutrino masses, we don't know everything, but we know, for example, the differences of some of them, we can actually start making predictions for neutrinoless double beta decay, and the next decade is supposed to be very, very exciting. Okay, so I think I've already overstayed my welcome, so let me just conclude. You don't need to look at any of this. This is just for the exam. But let me just conclude. The message I want to leave you with is that we've discovered something very, very interesting. Neutrino masses are not zero. This was not supposed to happen. This is a bona fide evidence of physics beyond the standard model, and we still have a lot of work to do. And we even know what sorts of experiments we need to do. We need to look for lepton number violation. We need to do precision neutrino oscillation experiments, and a whole bunch of other things which I didn't have time to talk about. And I just want to finish with this good-looking picture. In case you came here to listen about the Brave New World, you're probably very disappointed. So I do want to say something about the Brave New World. And I do want to remind you of that it turns out that the title of the book, which is a weird book that has aged in a funny way if you have read it recently, it's a dystopian future book. But the title of the book actually comes from The Tempest. And it comes from this particular quote here from The Tempest about the discovery of the daughter of the sorcerer that lives in the island. And she was very excited to learn that there's actually more people in the world than just her and her father. And you know, we're still in the process of figuring out this very exciting neutrino world. And we're also very excited about doing all kinds of experiments that will teach us a lot more in the next decade or so. So thank you. Sorry about going a little bit over.
So I will applaud on behalf of everyone real time without just the little emojis. That was great. The protocol for how we do now the questions is that people raise hand, and after you ask your question, then remember to lower your hand. And we will start with Aksa Shaikh.
Hello. Yeah, am I audible? Hi. Yeah. So apologies if I'm being too naive. I'm pretty new to this field. So there are a couple of questions that I had. One is that you talked about the fact that there could be a neutrino which has zero mass, right?
Right.
Pardon me if I'm wrong. Right.
That's completely correct.
Yeah. So, so I'm just confused that initially when we began to understand neutrino, we thought that it is massless, and then we found out that it does have mass, and now we are again going to a conclusion that it is possible that one of the neutrino might not have mass at all. So I am confused as like, why are we like, how did we decide that there could be a possibility that one of the neutrino might not have mass at all?
Right. So the reason is the only thing that we really know for sure is that at least 2 out of the 3 neutrinos have masses that are different from one another. And the reason is we only measure what's called the differences of the neutrino masses squared. So we measure, for example, m1 squared minus m2 squared, or m1 squared minus m3 squared. And we know what those numbers are. And nothing prevent, you know, so as far as those data are concerned, there's nothing that prohibits the lightest mass from being exactly 0, but there's nothing that prohibits it from being anything else. So from a purely experimental point of view, we can't affirm that the lightest mass is 0, and we can't affirm that it's not 0. So experimentally, it's still something that we have to figure out. I will say something for the more technically minded people, which is because we know that 2 of the masses are not 0, it is very unlikely to construct a scenario where the lightest mass is exactly 0. It's possible, but it's not so easy to do. But basically, the problem is because we haven't seen the effects of the masses themselves, we only measure something that's proportional to the differences of the masses. That's why we don't know whether the lightest mass is exactly 0 or not.
That's out of just out of possibility, right?
That's correct, yeah.
Okay. Yeah, and just another question. So there's one thing that you mentioned, that we can have more than 3×3 matrix, which means there could be possibility of having more neutrino. But then we know that a neutrino comes along with, you know, a particle like electron, muon, and tau. So are we looking at the possibilities of having more leptons in general, like in pairs, not just one?
That's a very good question. It's a great question. And the answer is the neutrinos are also special in this sense. So first of all, it is possible to conceive of the possibility that the neutrino comes along with a fourth family, which also comes along with a fourth electron. And the challenge with that is that from the self-consistency of our theory, if you start adding a fourth electron, you also have to add a fourth quarks and so on. So you need a whole fourth family. Exactly. And it turns out that that's ruled out by experiment. We have looked for a fourth family of other stuff, and we haven't seen that. However, the neutrinos are special. Because the neutrinos don't have any electric charge, it turns out that it's possible to add only neutrino particles to the model in a consistent way. We normally refer to those as stereo neutrinos because it turns out that they don't have any interactions other than the mixing with the standard model neutrinos. And so that means even though for the most part, it is easier to think about an extra neutrino that comes along with an extra charged lepton, that hypothesis is safely ruled out because we haven't seen an extra charged lepton. But it still remains the possibility that the neutrinos are, that there are more neutrinos that don't have a friend, a charged lepton friend with them. And this is special of the neutrinos. The other particles can't do that.
Okay, so that means we'll have to look at various ways to detect them, because right now we are, you know, depending upon the decay channels and stuff. So
the good thing is if there is a more neutrino states, and if those states also mix with the standard model interaction states, we should be able to see these heavy neutrino states because they talk a little bit to the standard model particles. And that's normally how we talk about constraining more neutrinos. If you invent a new neutrino that doesn't talk to anybody, we can't say anything about that particle. So that particle has to find a way to talk to other stuff.
Yeah, let's take the next question. Thank you, Eksha. Ronald Cohen.
Yes, I have two questions. One is, why don't we see neutrinos from the whole observable universe? Or maybe we do. And the second question is, can neutrinos be controlled?
So the answer to the first question is, we expect there to be a lot of neutrinos from the early universe. There's about 100 per cubic centimeter everywhere. The reason we don't see them is that they're very cold. So their energies are very small. And it turns out that the weak interactions are very perverse, that the cross-section is proportional to the energy when the energy is small enough. So the probability of seeing one of these neutrinos is super tiny. To make matters worse, because they don't carry a lot of energy, what you're really trying to measure is a very, very cold neutrino that doesn't interact very much, hits something, and gives it a super tiny amount of energy. So that means that detecting these so-called relic neutrinos is virtually impossible. It's been a question for a long time. People have some great ideas on how to do it, but I think we're still, I would say, a decade plus away from figuring out how to see these relic neutrinos directly.
Okay, what about from other stars? I mean, from all the stars.
That's a great question. So the neutrinos from other stars are not enough because the other stars are far away. Our best hopes are neutrinos from supernovae. And I showed you this picture of supernova 1987A. We've actually seen neutrinos from that explosion. We saw less than 20 of them. So we are on the lookout for the next galactic supernova explosion. And we have a bunch of detectors that are just sitting there ready and waiting for those neutrinos to arrive. There's a couple of other things that we see. It turns out that there's what's called the diffuse supernova neutrino background. These are the neutrinos of all past supernova explosions. We haven't detected those yet, but we have high hopes of seeing them in the next few years. So that will be very exciting, this diffuse supernova neutrino background. And the other thing that we have detected are ultra high energy neutrinos that come from super violent events like active galactic nuclei or blazars or weird astrophysics stuff. These are neutrinos that we think have some correlation with what's called the high energy cosmic rays. And we have built, there's this thing called the ice cube experiment in the South Pole. There's an equivalent experiment in the Mediterranean. These are kilometer cubed experiments that have seen a handful of neutrinos with a ridiculous amount of energy coming from somewhere. And we're still in the process of figuring out where that somewhere is. But the reason we suspected those neutrinos were there, it's because of the very high energy cosmic rays that we have observed in these gigantic, air shower detectors. So we suspected that there should be neutrinos associated to that. And indeed, we have recently, in the last few years, we have seen handfuls of those.
All right, thank you for that question. Let's take the next question by Sarah and John. Sarah? If not, next one is Andreas Reisenegger.
Hi, thanks. I actually wanted to ask about the astrophysical neutrinos. Have we learned anything about neutrino physics from detecting astrophysical neutrinos other than those from the sun? Or do we expect to learn anything from them?
Yeah, that's a great question. So first of all, yeah, the neutrinos from the sun, we learn a ridiculous amount from those.
Sure.
I mentioned this supernova 1987A. As I said, we saw under 20 events from that explosion, but we've written about 1,000 papers on that. And there's a lot of stuff that we've learned about neutrinos. One interesting thing that you can think about is we've learned, for example, that since the neutrinos got here from the supernova, they didn't all decay away into something else. And we learned that that means that the lifetime of all 3 neutrinos is actually quite long. And again, if only 2 of them decayed away, but one of them stayed behind, we wouldn't know about that. But if all neutrinos had disappeared, we would have discovered that by not seeing neutrinos from supernova 1987A. So there are certain properties of neutrinos that are associated either with a very long time, which we learned from, say, neutrinos coming from a supernova, and also the fact that the neutrinos have to traverse a lot of space to get from the supernova to here. And for example, in that process, let's say the neutrinos have to go through a lot of dark matter. Imagine that the neutrinos hit the dark matter and changed in some way. We would also know about that by looking at these supernova neutrinos. And finally, the last thing which I can say is, I talked about neutrino oscillations very briefly, but the neutrinos inside of the supernova also undergo oscillations in a very complicated way. So if we could measure the neutrinos arriving on the Earth and we could measure the different flavors, we could learn about how they're oscillating inside of the supernova, which in turn would teach us about some of the neutrino properties we haven't measured yet. So there's a lot of people betting on seeing these neutrinos from the supernova and learning both about the supernova explosion and about the neutrinos at the same time.
And is it expected that we could do that within the next few years?
If nature helps, we need to see it. The supernova has to go off. We don't control that. So this has been the big challenge. We can estimate, we need a supernova to go off in our galaxy. And the rate for that is about a few per century. Yeah. Let's say 1, 2, 3 per century. The Super Kamiokande experiment is a big experiment. It has been running for 25 years or so, and it hasn't undergone and seen a supernova yet. That means there hasn't been a big one in the last 25 years. But again, that doesn't mean that there will be one in 5 years. It just means that on average, you have to wait about 30 years to see one of those, or maybe 50 years. But we are definitely prepared. And we are very excited about the event, which will be the next galactic supernova, which has to happen eventually. and I'm hoping it'll be in my lifetime, but that's the plan. But we can't for that.
Yeah, let's take the next question by Sarah that was on the list but didn't reply earlier. Sarah Anjum. Sarah, you may have a problem with your audio, so I'll keep you on the list to fix your audio. We'll get the question from Yimeng Zong now.
Hi, thank you. So I have a question about, so you mentioned that one of neutrinos can be massless. And I was wondering if that's possible to can probe this scenario from the fifth force experiments.
So that's a good question, and the answer is not very likely. And again, what you're referring to is that you could imagine a force that's mediated by neutrino exchange.
Right.
And it's, to make a long story short, it's very difficult because you still have to go through the weak interactions to have this force happen, which makes the force exceedingly rare. And on top of that, if you're really talking about a force by exchanging fermions, you probably have to exchange a pair of them. That makes the force even harder to constrain. So unfortunately, we have talked about, people have speculated about forces mediated by neutrino exchange, and that would be very exciting. But we don't see how that would be feasible unless the neutrinos have some new force or new properties that we haven't uncovered yet. But it's clearly, it would be great, but it's very, very down the list of things that we think is feasible.
Thank you.
All right, let's take the next question by Ishwar Singh.
Yeah, thank you.
I'm sorry if I pronounce people's names wrong, but I'm doing my best.
So I just wanted to ask a very basic question. How are neutrino flavor eigenstates are fundamentally different from neutrino mass eigenstates?
So that's a good question. And the way to think about this is, at least the safest way to think about this is to think about only the mass eigenstates. The mass eigenstates are the particles. They're called nu1, nu2, and nu3. Now, when a neutrino is produced, for example, let's say that there's a pion decays into a muon and a neutrino. The question you want to ask yourself is, what was this neutrino that was produced? And was it neutrino number 1 or neutrino number 2 or neutrino number 3? And the answer is the thing that was produced was a linear superposition of neutrino number 1, neutrino number 2, and neutrino number 3. Because the neutrinos are always produced in these linear superpositions, we find it very convenient to give them a name. So the linear superposition of 1, 2, 3 that's produced when the pion decays into a muon and something else, we call that a muon neutrino because it's a shorthand for a linear superposition of nu1, nu2, and nu3. So I think that's the safest way of thinking about that. And if this sounds confusing, but you know something about particle physics, the exact same thing happens with the quarks. For example, when there's a decay of a W boson into a charm quark, you ask what's the other quark that gets produced, and strictly speaking, the other quark that gets produced is a linear superposition of down strange and bottom. Now, the reason we don't usually talk about that is because the masses of the down strange or bottom are so different that this linear superposition that gets produced isn't really coherent. It decoheres absurdly fast. So we normally like to talk about the fact that the charm gets produced with a bottom quark with some probability, or the charm gets produced with a down quark with some probability, and the charm gets produced with a strange quark with some probability. But it's a different manifestation of the same phenomenon. And we normally don't give the linear superposition of down strange and bottom a name. Even though we do give it a name, it's called a strange prime. But we usually don't talk about the strange prime as a particle. And it's the same with the nu e, nu mu, and nu tau. They are not particles, they're linear superpositions of particles. I hope this is...
All right, so let me ask the question by Sarah. She sent it on the chat because she's probably having a network problem. So the question is, can you say something about sterile neutrinos and whether it is possible that the oscillations can go through more eigenstates of the type of sterile neutrinos?
Yeah, so that's a very important question because it's something we pay a lot of attention to. So again, the picture you want to have is, let's see if I can find some picture. So if you look at this picture here, you know, the one with the mass eigenstates in these colors, when we talk about more neutrino states, the simplest picture to have is that you're really adding more mass eigenstates. So you're adding, for example, a neutrino number 4, and a neutrino number 5, and a neutrino number 6. And the question you're asking is, okay, so if I have a neutrino number 5, what's the probability that that will interact with the electron? Or what's the probability that that will interact with the muon? And that's the question that we can get an answer to. If those probabilities are not 0, these new mass eigenstates will also contribute to neutrino oscillations. So the way that we look for these so-called stereoneutrinos is by looking for new oscillation frequencies and new amplitudes associated with these oscillation frequencies, because we can always talk to what we say is the active component of these extra mass eigenstates. So that's how we hope to be able to see new neutrino states, in spite of the fact that they may not, you know, the stereo component of this neutrino may not have any interactions at all, is we always get to talk to the active component of these new mass states. So what we're really always talking about is, are there more neutrino mass eigenstates? And do those neutrino mass eigenstates talk to the electron, the muon, and the tau a little bit? And we do a lot of experiments looking for those for lots of reasons. One is that we may have some evidence for them. It's very weak, and it's we're still figuring that out. But the other one is that when people construct models, for example, to explain non-zero neutrino masses, sometimes you predict the existence of new neutrino mass states. So looking for those is a great way of checking if a particular idea for how neutrino masses come about is actually correct.
All right, so we have a few more offline chat questions that were related to Patty. George Matzes. So the question is, how is basically, if the neutrinos are Dirac or Majorana, what is there should be an impact on the energy of the 1K background cosmological neutrino thermal bath. He states by a factor of 2. Is this correct? And is it too small to be observed?
Yeah, so this is a great question. What happens is, if you could measure this relic neutrino background, and the neutrinos who are Majorana or Dirac, the flux that you expect is different by about a factor of 2, which is a big effect. So if we could see this relic neutrino background, in principle, it would be, in many quotes, easy to determine if the neutrinos Majorana or Dirac. Clearly, since we haven't seen the relic neutrino background, for now, this is not a useful question because we haven't seen it, so we don't know if it's 2 times bigger or not. There's another challenge, which is, in order for you to say whether the answer is 2 times bigger or not, you have to know compared to what. So you have to know the density of the relic neutrinos, which it turns out we know quite well, except that we need to know the density of relic neutrinos here on the Earth and not on average in the entire universe. So the question is, how well do we know that? And I think we can claim to know that fairly well, but it is a number that people worry about. Special people who worry about large-scale structure calculations and galaxy formation and stuff like that, they try to ask if we can calculate the density of neutrinos here on Earth very precisely. And the answer is yes, but they still worry about a few things. So we think we should be able to know that number at the tens of % level, which would be enough to see a factor of 2. But I think the jury is still a little bit out on that.
Then we have another offline question from Sadashev about the mixing matrix. Which kind of invariance is it following? Is it Lorentz invariant? Is it Poincare invariant, and why?
Yeah, so the mixing matrix is an everything invariant. It's a coupling. So the way to think about the mixing matrix is the elements of the mixing matrix are just a hidden way of talking about how electrons, neutrinos couple to the W boson. So just like the electromagnetic coupling is not something that changes when you do a Lorentz transformation, these mixing matrix elements also don't change when you do a Lorentz transformation? It's a good question.
Yes, and one last question I have offline, I have from the chat through parties from Megan Donahue. What about the gray diagonal line that doesn't go through the same point? And I'm not sure what is the gray diagonal. And I have two more raised hands, well, one more raised hand that we're gonna go through next. But let's try and figure out what's the
that's
diagonal.
a good.
It was in the quarks.
Oh, thank you. So it's this great picture here.
That was the
Yeah. So good. So this gray line here, that's actually not allowed. That's excluded by some experiment. And sometimes so what happens is because some of these things are expressed as angles, sometimes there's some degeneracies that you don't know if you've measured, like the angle or pi plus the angle or pi minus the angle. So some of these curves correspond to different possibilities for the same measurement. And that's kind of what's going on there. Yeah, thank you. There might be a slightly more clever answer to that gray area, but I don't remember.
Which experiment is it? Where is this excluded from? We have to.
I don't remember.
That's yeah, I don't remember myself.
I wanted to say it has something to do with sin 2 beta.
Yeah, it has to do with
sin 2 beta. But I could be way off.
Maybe one of the B physics experts, experimental.
It could be some degeneracy in extracting sin 2 beta, and then we rule that one out. But don't quote me on that. That could be wrong.
Okay. Yeah. And we have one more raised hand. It's Powen Chang. Oops. Yes.
Okay. Thanks. So I have a more question. Suppose we detect a bunch of mu-e from an unknown source. Can we distinguish whether it is directly produced from the source or actually it comes from the oscillation of nu mu or nu tau?
Good. So the answer is we can't. So basically, if you place a detector somewhere and you count electron neutrinos from some mysterious source, you can't really determine if the source was a source of nu-e's, or if the source was a source of mu-1 neutrinos that have oscillated into nu-e. And then, of course, you have to qualify the question by saying that maybe your detector can only see nu-e's, and that's why how you ended up in the situation. But the reason the only thing I want to add is that for these experiments to be useful, you really have to understand your source very well. And there are lots of ways in which we do that. A very clever way in which we do that is we actually also put a detector very close to the source. So even if we don't trust what neutrinos are being made in the source, by measuring the neutrinos very nearby, we can really be confident that, when you measure something nearby, you don't give the neutrinos enough time to oscillate. So by measuring the kinds of flavors that you have nearby, you're pretty confident that you understand your source well enough that when you see the new flavors appearing very far away, you're very confident that those neutrinos are a consequence of oscillations and not just a consequence of the fact that you don't understand your source very well. But yes, understanding the source is a necessary condition for doing any of this.
Thank you.
We have one more relayed through Patty again from Papitra Sen. Since you invoked Lorentz invariance and rest frames, do you need to embed SU3 in SU6-1?
I hope the answer is no.
I hope so.
But maybe you mean something else. So for everything that I've been talking about, we can happily explain all of these phenomena by sticking to the standard model gauge interactions, the SU3 cross SU2 cross U1. And the only challenge, which I didn't get to talk about, is we need to have a mechanism through which the neutrinos acquire mass. Just like, the electrons and the top quarks, they get a mass through the Higgs mechanism. There's some mechanism that gives the neutrinos a mass, and that's where we screw around with the theory. But the screwing around doesn't necessarily require that you add more gauge interactions, if that's what you're referring to.
And we have one more from Keith. who is, or well, we have two more. Let's go to Keith's first to understand how the mass states and the flavor states operate in the process of oscillation. The way he wrote his question is, as the mass states travel at different velocities, would the flavor states separate spatially into their constituent mass states after a long enough time? So
that's a great question, and the answer is yes. And basically, every time I was discussing all of this, I was kind of cheating. And if you want to do a proper discussion of this phenomenon, what you really worry about is, so again, I said, when a charge current process occurs, the state that gets produced is a linear superposition of nu1, nu2, and nu3. The key question that we have to ask is that linear superposition really a pure quantum mechanical state? Or you know, is it a coherent superposition of 1, 2, 3, or does it come out as an incoherent superposition of 1, 2, 3? If we have oscillations, it has to be a coherent linear superposition. And it turns out that for all the sources that we know about, the neutrinos are produced coherently. But as you're mentioning correctly, the coherence can be lost as a function of time. So if you wait a very long time, at some point these mass eigenstates will separate, and then you no longer have a coherent superposition of nu1, nu2, and nu3, but you actually have a classical mixture of 1, 2, and 3. Now it turns out that this decoherence time for all the sources that we know about is quite long. So we've never seen this decoherence phenomenon happen. But in principle, it's there. And what you describe is exactly one way in which they can lose coherence, is because in reality, these states have slightly different velocities, so they can physically separate and lose coherence in physical space.
Well, this answers also Yuhao Sun's question about the coherence or coherence of neutrinos and quarks in the same sense. And there's another question for Plum and Krastov. Aren't there experiments that can rule out sterile neutrinos?
Ruling things out is very hard. And the problem is the sterile neutrinos can always be made invisible. And again, remember that the thing that we measure are these mixing angles with the heavy states. So if you make those new mixing angles very small, you can really effectively decouple the sterile neutrinos from the oscillation phenomenon as a whole. So basically, you can only look for the sterile neutrinos when they couple enough with the ordinary neutrinos. What we normally talk about is there are sterile neutrinos that we care about because they do something. You know, we don't just invent a random sterile neutrino. We invent a sterile neutrino that does something for us. And those we can try to rule out by doing oscillation experiments. So in reality, right now, we are in the process of checking the hypothesis that there are sterile neutrinos with certain properties because we think they are good for something else. And there are, for example, several experiments at Fermilab that are turning on right now that aim at addressing whether these sterile neutrinos exist or not. There's a whole bunch of other experiments monitoring the neutrinos that come out of a nuclear reactor to look for these sterile neutrinos, also in the hopes of testing a particular kind of sterile neutrino that does something very specific that we think is useful for something else. So that was a very long answer, but the answer is yes, we're working on it, but we can't rule out the idea of sterile neutrinos, but we can rule out phase, parts of the sterile neutrino phase space that hopefully are good for something.
All right, with this, I think we have arrived at 11:30 Mountain Time. Let's thank André again. I am applauding with audio, but everybody else can use the emoji if they want. Thanks everybody for attending, and thanks everybody for posing the great questions, and Patty for helping relay all these questions, and the Aspen Center for Physics. Next week, there's Dark Matter coming up with Kimberly Brody from Johns Hopkins. So we'll see everybody there then. Thank you.
All right, thank you.